Okay, so this is the outline of chapter 25 about the capacitor. Okay, so first we will introduce what is a capacitor and then try to compute some of the capacitance with some geometric shape, okay? And then we will talk about the parallel series capacitance, so the equivalent capacitance due to parallel and series capacitors. And then talk about the energy stored in the E field or energy stored in the capacitor. So because the capacitor, actually we have learned the structure of the capacitor before in chapter 22, 23, when we learned about how to calculate the E field between the parallel plate. Okay, so we will generate a constant E field between the parallel plate. And actually, as much as this structure generate E field, it stores some energy in the E field. Okay, and then finally we talk about the capacitor with dielectric. Okay, so which will modify the Gauss law a little bit. Okay, changing the epsilon to be an epsilon. Okay, so but yeah, that is just a minor modification, at least for this course. We will not try to make it more too complicated. Okay, so this is the definition of a capacitor. So so for capacitor, it consists of two isolated conductors. Okay, so in this case, the plate. Okay, so but it does not necessary to be two parallel plates. Okay, it can be a sphere. Okay, it can be in other shape. Okay, with a charge plus Q and negative Q, its capacitance C is defined from Q equals CV. Okay, so this is very, very important, even though our daily research still use this simple formula. Okay. Yeah, so actually, where is V is the potential difference, or usually in a circuit sense, we will call this one voltage. Okay, sometimes I just call it voltage, but in this textbook, on a physics point of view, try to call it potential or potential difference of we usually call it the voltage or voltage difference between the plates. Okay, so here it says, okay, so if we have a charge, okay, so let's say we have a positive charge on the top plate. I don't try to draw too much. Okay, so and then we have a negative on the bottom plate. So in that case, suppose we have a positive charge on the top plate. Actually should be uniformly distributed. Yeah, but I'm too lazy to so that. Okay, so but at very least, okay, the idea here is yeah, it will generate E field uniformly, at least close to the center. Okay, close to the center. If it is near the edge, it tends to be a bit weaker. Okay, and there will also be some fringe. Okay, some fringe electric field line. Okay, outside. Okay, yeah, but relatively weak. However, later on we will actually fringing, using the word fringing. But later on, we will make a simple approximation. Okay, because we are engineer. Okay, we are engineering student, so we tend to make things easier, or make life easier. Okay, so usually we try to approximate it as, okay, suppose we have a negative, we have positive. Okay, so we will assume in this whole region, we have constant E field. We have constant E field. Of course, from positive side to negative side. And then inside the whole region, we assume all the E field are constant. Okay, E field are constant. And outside, E field to be 0. E to be 0 outside. E field to be 0 outside. Okay, we will make this approximation. Otherwise, okay, we need to care about, okay, this part is weaker, how weak is it? And then if we integrate it, okay, we need to integrate a non-constant function, okay, which makes things much more difficult. But if we try to integrate a constant, it's just like a multiplication. Okay, so this is what we like. Okay, so here is a simple circuit with this capacitor. Okay, so this is very crappy, just placing two conducting plate here. Okay, and then here we have a battery, we have a switch. We have a battery, we have a switch. So we try to, let's say we can just put this button down, okay, so that the circuit will close. Or if you don't push the button, it is just open, then there will be no current going through. Okay, so of course this is a figure. Okay, so if you need to draw the battery, need to draw the switch every time, this is time consuming. So we will use some circuit symbol. Okay, probably you should have learned it in high school. So this is the battery. We have two parallel lines, but one is longer than the other to represent a battery. Okay, whether the shorter one is thicker, it doesn't really matter. Usually you will just draw two parallel lines, one is longer than the other is sufficient. Okay, so and then the longer line represent the positive terminal, and then the shorter one represent the negative terminal. And then this is the switch. Okay, so this is the switch, this is the capacitor. Just draw two parallel lines with the same length. Okay, so try to distinguish these two. Okay, so if one line is longer than the other, it's the battery. If two lines are with the same width, then with the same length, then it's a capacitor. The gap in between doesn't really matter. You can draw it closer together. You can draw it something like this. It's still fine. Okay, the distance between the two lines, it doesn't really matter. Okay, so yeah. So this is just a very simple circuit setup. If this switch is open, then there will be no current. There will be no current. And no charge on the capacitor. But if you try to close the circuit, then there will be charge accumulate on this plate, and then there will be negative charge accumulate on the other side. Yeah. Okay, so here we try to calculate the capacitance with some structures. So first by working on this parallel plate structure. So here calculate E field and potential difference. So of course we need to make use of the Gauss law. Okay, so you see this symbol. Okay, you see E dot dA, it is Gauss law. So applying the Gauss law, we need a Gaussian surface. So here, suppose this is a cross section of a parallel plate. So you only see two bar there. Okay, but actually this is a two parallel plate. In this direction. Okay, so here is the Gaussian surface, which is a rectangular box. Okay, rectangular box. Okay, of course in 3D, but in this direction, it is clearly that there shouldn't be any E field. Okay, so for this Gaussian surface, for these two sides, okay, this size is inside the top plate, okay? So which means that the E field inside is 0. So this side won't contribute, okay? This side won't contribute. This side is actually also outside the capacitor, so the E field is also 0. So the final stuff, okay, is actually this part. Okay, just as what I mentioned, we already assume that the E field between the parallel plate are constant. So which means that E field are constant here, and then also the top plate is positive, and then the bottom plate is negative. So the E field is pointing downward. The E field also. The E field is actually all the way pointing downward. So actually, we would like to integrate from this I, from the negative terminal to the positive terminal. Okay. So here we have a Vf minus Vi equals to E dot ds from I to F. Okay, this is just a definition in chapter 24. Okay, in chapter 24. Okay, but here we try to a little bit simplify it. We try to change the axis ds, or at very least, or maybe actually not change the axis. It is like actually if we like to integrate from I to F, which means that ds is pointing upward. Okay, ds is pointing upward. And then the E field is pointing downward. So which means that actually the I is a negative. I is negative. F is positive. Okay, so nothing special here. But this one will be like E times ds cosine of 180 degree. Okay, so this one is negative 1. Okay, so this negative 1 and this negative side cancel each other. Or multiply to be a positive 1. So finally, we only have E times ds here from the negative to positive, just to make it without a negative sign. Okay, nothing special here. Okay, so the next is to apply the Gauss law. So just as what I mentioned, okay, this side, and also this side, it don't contribute. Okay, so finally, integrating E dot ds for this one. Okay, E and dA. Okay, so E and dA. E is E is pointing downward. Okay, also dA is pointing downward. Okay, because it should be pointing outside. So E and dA are parallel to each other. So E dot dA is E times dA, and E is a constant. So what I mean is this one turns out to be E times A. Okay, it is nothing special. Okay, it's just a multiplication. E is the constant inside the region of the between the two parallel plates. Okay, and then A is the cross-section area here. Okay, A is the cross-section area here. Okay, of the capacitor. Okay, so it turns out to be epsilon naught times EA to be Q. Okay, Q is the positive charge. Okay, because this Gaussian surface only encloses the positive plate. Okay, so this is positive Q. Okay, so in the previous page we have V in terms of this one. So we have E is a constant. So we just move it in the front to the front. So E times this one from negative to positive, which is the distance between the negative plate and positive plate. So this integral is nothing but small d. Okay, so finally we have V equals ED. Okay, V equals ED. Combining with this one, we can actually eliminate E. Okay, by this one we can have E equals V over D. and then putting it to here. Okay, so we have epsilon naught V over D times A equals Q equals CV according to the definition of the capacitor. Okay, so this is the definition. This is the definition. So CV. Okay, so finally we can actually cancel the V. So finally C equals epsilon naught A over D. So which is a very, I would say this is quite elegant. Okay, so C is actually this one is the permittivity constant, so 8.85 times 10 to the negative 12. And then this is proportional to the area, proportional to the cross-section area of the capacitor. So if it is the cross-section area is larger, then the capacitor is proportionally larger. And then inversely proportional to the distance. Okay, so if you want to make the capacitance larger, then you need to make the gap between the plate shorter and shorter. Okay, then you get a larger capacitance. Okay, so this is the capacitance of parallel plate capacitor. So the next case is a cylindrical capacitor. So just as what I mentioned, capacitor doesn't necessarily to be parallel plate. It can have other structure. So one common structure is the cylindrical capacitor. If you have ever, like assemble your computer, probably you have seen or many like the cylindrical capacitor on the motherboard. Okay, 那些叫做电解电容。OK， 电解电容。Okay, on the motherboard of the computer. Okay, so actually those 电解电容 have polarity. Okay, if you connect it in a reverse way, okay, then it will explode. 就是那些电解电容的话，就是它的正负极是很重要的。如果你反过来接的话，它会爆炸的，但它不会炸得很厉害，它就是像。比如说，像你拿起一叠书，然后你放手砰放在地上，就会有砰一声，然后它会有一些类似肉松的味道 ，OK， 就是，但我自己没有炸过，就是以前大学做实验的时候，有同学就会炸过，就是通常就会有这种声音跟气味这样 ，OK。So anyway, so for the cylindrical capacitor, so in the cross section, a cylindrical capacitor of length L, okay, formed by two coaxial cylinders of radii A and B. Okay, so this radii is the plural form of the radius. Okay, radius is one is only one. Okay, radii means radius A and radius B. Okay, so radii A and B. Okay, so we assume that L is much larger than B. Okay, what is L? L is the length. Okay, L is the length. Okay, so suppose we have a cylindrical capacitor. Okay, usually like this. Okay, usually like this. Okay, like this. One leg is longer, one leg is shorter. Okay, so longer legs means this is a positive side. The shorter leg means that is the negative side. Okay, so don't try to mix up. Yeah, 但是你知道为什么大学做实验的时候有时候会炸？就是有些人就是把长的角剪短，剪成短的，然后放回去那个盒子。那下一个拿的时候，他就会搞混，他就没有看那个他也许在上面会写着这个是正的，这个是负的。但是一般的话，就是长的那个是正的，短的是负的。那有人剪了长的是放回去的话，那下一个就会炸掉。Okay, so this is like so actually inside. Okay, if you try to look at the cylindrical capacitor on your motherboard, you cannot see what is really inside. Okay, it actually packed well. Okay, because if you you don't want you to touch what is really inside, okay, but actually there should be a inner, okay, inner cylinder and the outer cylinder. So the inner cylinder with a radius A, okay, the outer cylinder with a radius B, okay, so this is a cross section, so which means that, okay, this A is this one, okay, this B is the outer radius. Okay, so we assume that L is this part, okay, L is this part. So L is much larger than B, okay, so this is quite long. So that we can neglect the fringe of the electric field that occurs at the end of the cylinder. So each plate contains a charge of magnitude Q, okay, charge of magnitude Q, charge the field magnitude E is related as this one, okay. So the idea is, of course, we still use the Gauss law, okay. So what is the Gaussian surface? The Gaussian surface is here. This is the Gaussian surface. Gaussian surface, okay. So of course it is a cylinder, okay, but the top side and bottom side won't contribute because all the E field, okay, all the E field are like in radial direction, okay, all the E field, okay, so all of these are E field, okay, so it won't go in this direction or that direction, okay, so those two sides won't contribute, so only this side contribute, but of course you keep in mind that this is a cylinder, not just a circle. Okay, so anyway, okay, as much as and actually also sorry, actually we try to assume that the radius of this cylinder is small r, okay, this small r is actually between A and B, and actually this is symmetry, okay, because this is actually a circle, this is another circle, this is also another circle, but all the circle with the same center, okay, so we call them the coaxial 中文叫做同轴啊，同轴的意思就是你的 cylinder 的话，就是每个圆这里有个轴嘛，这个是 axis 嘛，所以它们三个的轴都重叠在一起，叫做同轴 coaxial. Okay, so all the axes of the cylinder are overlapping. Okay, are overlapping, so that they are called coaxial cylinder. So here, okay, as much as they are coaxial, so which means that this is altogether symmetry. So the E field and the dA are actually parallel to each other. Actually, E and dA actually parallel to each other, which means E dot dA is nothing but E times dA. Okay, so E times dA and then integration. So this is nothing but the surface area. This is nothing but the surface area, and then times the E and then epsilon naught is the Q. Okay, so we assume that the inner radius have the positive charge and the outer radius have the negative charge. So in this case, E times A. Okay, what is A? A is the cross-section area, so which means that we try to cut it out, okay, cut it out like this and then expand, okay, so this rectangle with the height L, okay, just as here, okay, with a height L, the width will be the circumference of this circle, which is 2 pi r. Okay, so here we have 2 pi r L here. Okay, so Q equals this expression, and which means that we have E equals Q over 2 pi epsilon naught r L. Okay, so we just have the expression from here to here. Okay, and then we try to plug it there. Okay, so we have a V equals integration of with the same form, okay, with the same form, it doesn't change. So because we already mentioned this one for almost all the structure, okay, as much as you try to define apart from the negative terminal to the positive terminal, okay, then we can always eliminate the negative side. So we try to put this one here. Okay, so here we have a q over 2 pi epsilon naught L, and then ds. Ds is actually like, for example, this. Okay, this is S. Okay, sorry, S. Sorry. S shouldn't be like that. Okay, this is our direction. Okay, this is our direction. But S direction is the reverse case. Okay, S direction should be start from the positive side to the positive side. So S direction is actually opposite to the our direction. So which means that we need to have a negative sign to change ds to dr, because s is negative of r. So taking the derivative on both sides will be ds equals negative dr. So we come up with a negative sign in the front. Okay, other variables remain the same. So q 2 pi epsilon naught L, q 2 pi epsilon naught L. Okay, because we have dr, so this r remain in the integral side. So we have integrating dr over r from b to a. B is the outer radius, which is the negative terminal to the a. Okay, but actually a is smaller, b is larger. So finally, this negative sign, if we provide to the lower upper limit, it will swap the lower upper limit, make it a positive value. So finally, it turns out to be something like q over 2 pi epsilon naught L lateral log of r evaluated from a to b. Okay, absorbing the negative side, okay, to swap the lower upper limit. Okay, and then log b minus log a, lateral log of b minus lateral log of a will be lateral log of b over a. So lateral log of b over a. So v equals this expression. And then finally, c will be q over v. So q is here, v is here. So which means that we move this to the right side and then move all the other to the other side. Okay, so finally c equals q over v, which is 2 pi rl. Okay, here is bottom, go to the top, and then this is on top, go to the bottom. So c is have this expression for the cylindrical capacitor. Okay, so let me finish this off. Okay, so so this cylindrical capacitor, of course, this one is a constant, nothing special. And then L is the length. Okay, so if you want to have a larger capacitance, you make it longer. And then if you want to also make it longer, you need to make the denominator smaller to make the capacitance smaller, to make the capacitance larger. Yeah, to make this log smaller, which means that b over a should also be smaller. Okay, so which means that b over a is small to make large c. Okay, so which means that still you need to make the gap between the two cylinders narrower and narrower to make the capacitance larger, and also you make it longer so that the cross-section area is also larger to make the capacitance also larger. So yeah, also even though they are not the same case, but generally the idea is the same.